And we are back live. Unusual schedule today. Surprise stream. I'm not really sure what the new schedule will be, and we'll definitely have a new schedule. Yeah, I will try to figure something out, something reliably doable. But for now, probably a lot of, what do you call them, guerrilla, ninja style, whatever, surprise streams. In any case, let's focus on today. And what we're gonna look at today is our first steps to learning more about not the language itself, but the infrastructure around it, and a bit for the language itself. Because the hardest part about learning a new language, I guess languages in general, not just programming languages, is not the specifics of the language, the stuff we've focused on so far, and more the how do you practically use it, what code is already out there ready to use. Like what phrases exist, what metaphors are there, what is already out there that you can just make use of. Before we get to that, however, let's make a quick recap of how we store data, large amounts of data. We've done this recap already, and I think I'm spiking in audio. Let me turn this, maybe just put the microphone a bit further away. We've done this recap before, but let's do it a third time now, maybe? Usually, if we have a variable, we have a single value. That's one number, exclusively. If we want to store two numbers, we have to use two variables. But variables have to be declared one by one in code. If we are not sure how many numbers we need, or if we just have a lot of different numbers, that's rather inconvenient. And the oldest method, we know how to, let's keep that in the namespace. The oldest method for storing a lot of numbers that we've at least talked about on the stream is with a linked list, where it's just called item, which internally references another item and a value. And so I can have item A equals a new item, and a dot value could be 1, and a dot next could be new item. So another item create, and a dot next dot value could then be 2, a dot next dot next. It's another new item, and we just chain them all together, which we could do in a loop instead of writing this out by hand. And we can also read the data out. Just store that in a variable, or a dot next dot value, store that in a variable, and that too we could do in a loop. And that's I was about to say valid, but it's more than that. It's a useful way to storing data. And it's an active use for many situations because it has some really cool advantages. But the biggest advantage for us right now is accessing items in this big list is a bit cumbersome, because if I only have item A, the first one on the chain, getting to the last one on the chain takes a bit of time. I need to go through all the elements in between. So getting data out can take a bit of time. And the memory I need is significantly larger, because I don't only store the data itself, I already require space simply for the reference to the next item. Even if I don't store any data, this will still take up space. We have overhead. besides the data we need to store, we also need to reserve space for the references to the next object somewhere on the heap, which will contain a value and another reference to somewhere on the heap, and so on and so on. And so for a slightly different way to access data, we have the idea of arrays, which are also somewhere on the heap. But instead of storing that as different objects, we simply say reserve space for integers and only integers. And we tell it beforehand how many we need. Reserve space for 10 integers exactly. And those now all exist on the heap in a neatly, tightly packed box with a little bit of overhead, sure, but generally we only require as much space as we do for the actual data. And we can now access data in here directly using the index, just the offset basically from the very first address where we start the array. So it's easy to access data, it's very compact, we don't have any overhead or extremely little overhead, especially if we make very large arrays, then compared to the size of the data, the overhead is nothing. So it's very efficient and very convenient. But of course it has a downside too. It's that this 1000 now fixes this array to 1000 elements, meaning we cannot have any more than that. We don't necessarily need to use all that space, sure, we could always reserve more than we need, but then we might just waste space anyway, so linked list might have been better. And if we do need more space, well, tough luck. This array cannot be extended anymore. We can't simply tell the system to add some more space after the array in the heap, because that might already be occupied. Instead, we have to create a new array, array2, which is a new int array, and we can make it as big as the old array, plus whatever more space we need, maybe just 1. And int, that's better. And now we can copy over the data, int I equals 0, less than length plus I. We just iterate over the old array, and we'll copy the data from the old array into the new one in the exact same location. And all the additional spaces, well, additional space, we only expanded by 1, is free for us to use however we like. So array the length would be the new free space, something like that. Writing this code out every time we need to expand our array, that's not the greatest way to do that. We can simplify things a bit if we use a method for that. Let's make this static, because, well, generally you don't have to make methods static, but it has advantages. So in this case, we don't need to tie to any specific object. We don't tie to any variables that are exclusive to a specific instance of program. Anyone that sees program can use this method. So let's keep it at that. It's not returning anything. Let's make this clever. Resize, we call it. And it will receive an array, but it will receive a reference to the array. If you remember the ref keyword, essentially, when I'm now calling resize with array inside, well, let's put it like this. If I use just the classic way, with array directly, we copy the value of this variable, which is just the address of this array on the heap. Keep in mind this is an array, so what we store in this variable is the very first address at which this array starts, but the array is stored on the heap. But we take this first address and copy that value of this address, just the address, over to the method here and copy it into this variable. So we have this variable on this method, this stack frame, and we have this array variable on this stack frame. They both have the same value, the same address pointing to the same array on the heap, but they're distinct variables. If I change this to say null, then this original array will still point to the original real array. So distinct variables, nothing I do here affects this variable. I can, of course, change the array both point to, but that's a different topic. By doing this as a ref, however, I'm not creating a new variable and copy the value over. I'm not telling the system, use the same variable. Basically, this array is on the stack, in this stack frame, and we tell the system now, when you run this method, make sure that array, this variable array, is also pointing to the exact same location on the stack as this variable. They both reference these variables are the same location on the stack, and the one value this location on the stack contains is an address to the heap. So you have to go a bit indirect. This is a reference type, it's an int array, so it's an address for the heap. But by making it ref, we expose that variables themselves are also just addresses, but on the stack. Well, I mean, I guess if it's a variable inside a class, so it's a field, that's a special case. In that case, it can be on the heap or on the stack, depending on if it's valid. Never mind. Anyway, by calling it ref, if I change array in here, like that, then array is also changed up here. This array will now be null, because I'm referencing the same variable, right? And that's an advantage, because now we can also add, and let's make it simple, just call it increase. Let's wait, what am I doing? Wait, why is it not? Oh, I'm an idiot. I'm an idiot. Should have made the declaration in the method definition and not the method call. It's warm. It's really, really warm. It's warm with a capital HOT here. I shouldn't use that as an excuse, but I'm unable to find something better. Yeah, but that means we can now create the new array, which is the same as before. We use the array.length of old plus the increase, and then we I equals 0. We copy over the old stuff, and let's then array.length. Say new array I is the old array I, like that. And then we say array is equal to new array. So right now we have an integer array with 1000 elements. And that is referenced by this variable array. But once we call this resize method, actually let's quickly do this. Size length. So in the beginning we have 1000 elements in here. Then we call this resize method and then get the length again. Run this real quick. You can see that the size changed from 1000 to 1001. Because we passed this in as a ref, we can change this variable directly, which makes the whole thing a lot more convenient. We can now sort of resize the array. Cool. it's still a bit annoying that I constantly have to think about, do I have to resize this? Is it big enough for what I'm doing? Do I need to call this method again? Maybe you can do away with that as well. And when we do that, we can do something more for the efficiency. We'll get to that when we get to that. So our first step was to just offload the logic into its own method that we can call again wherever we need it. And using the ref keyword, we can make it very convenient. If we want to keep track of, do I need more space, then resize. If we're still in the clear, don't resize. That requires us to store the information how much space we are already using of this array. Like maybe I'm only filling the first 10 elements and then we still have 990 left to use. Or we already had 999 elements and I have 2 more to add, then yes, I will need the resize. I somehow need to keep track of how much space is actually used in this array. That means we need to store a piece of information somewhere that's linked to this array. And the most convenient way for us to do that is with a new class. For now, let's call it growing array. Or not growing, let's call it resizing array. And to make sure we don't accidentally change data from the outside, we're gonna make the actual array private. Call it array. And we're also gonna, for now, let's keep it just private and store in a field how much space we're actually using. So let's call it size. That's the real size of the array as we use it, not the total length of this array in memory. So size has its own meaning. That's just how much space do we really use in this array so far. Let's make quickly a constructor and create a new array with just 0 elements. Ignore the green squiggly line. That's because it suggests a different approach for this. A slightly more efficient approach. And sure, we could do that, but you wouldn't understand that yet. Maybe by the end of today's lesson you will. So we'll just pretend it's not suggesting something more efficient. And size, of course, starts off as 0, because we're not using any elements so far. Well, we have an issue now. The array is private, so how do we store data? We could use a simple method, public void set value. Could give it a value and index, which will set the value at a specific index, and index equals value, like that, for example. And to read something, we could do public int get value, like that. And index will just return array index, like that. And in theory, this is already somewhat functional. The only problem is our array is right now 0. So no matter what we pass on as index in these two methods, we'll get an exception because we try to access data in an array that doesn't exist. Or as position, we access a position inside the array that doesn't exist. So maybe add something that lets us expand the size for the array. And add is actually a good keyword because when we start off with nothing, let's just remove this and create a new resizing array. When we have nothing so far, Well, we want to add something. With an array, we already start off with a certain number of elements. We don't have to add anything, we don't remove anything, it's just always there. But this is closer to a linked list, where we start off with nothing and then have to slowly add stuff. So instead of setting or getting, we can public void add and value. And now we can simply say, this is a value we want to store, put it in the next free spot in the array. So we can check through size, how many spaces in the array are we using. And that means that is also the index for the next free spot in the array. And this is actually the wrong shortcut, so it doesn't work like that. But okay, let's do array manually like that. So in the beginning, size is 0. So that's the very first index we could access. Like this. And once we edit the data, we increase size, which I'm gonna make with the increment, like this. Or we could, of course, go like that and do it in one line, but let's do it in two, just to keep everything a bit more separated, easier to read. So resizing array.add 1. I could call it again with 2 and 3. And I could do resizing array.setValue. Maybe index 1 will be set to 20. And we can do resizing array.getValue, index 0. Like that, to get the value back. All well and good. The only issue is that even though we have a method to use up the space now that is already in the array, what do we do when the array is full? Like it is right now. We have no space for any elements, so the very first time we try to add something, the array isn't big enough. Well, we're gonna have to add our resize method again, and we have to make sure that our array has enough space when we add elements. So if the current size is greater or equal to array.length, then we need to resize. So if you think about it this way, just always use the smallest examples. If you're not sure about the off-by-one stuff, array length is right now 0 and size is 0. And in this situation, the array has no space for any elements. So we need to resize the array. So the length being equal to the size means we have to resize. If the array was length 1, so if the size was less than the array length, well then size would be index 0, which is a valid index in this array that starts at index 0 and also ends at index 0. So that is fine. Being equal, that's an issue. And if the size was bigger than the array length, then we also would have an issue. Actually, we have multiple issues because why is the size suddenly bigger? Something must have gone wrong. I'm just gonna catch both cases and say if the size is bigger or equal to array.length, so if we already fully filled out the entire space the array offers us, then we need to resize. And we can do it the same way we did before. New array equals new int, and we're going to do that to size. Plus 1. Command off by 1. We want size to be less than the array length. So the next best value is 1 added to size. And now the new array.length will be greater than size. So size can point to the position in new array. We'll just go through the entire loop again. Array.length. And we're going to copy over the stuff into new array from the old array. What is going on? Why can't I? Better. Like that. And then we're going to say array is equal to new array. So the same stuff we did before, just put into this branch inside this method. Let's set a breakpoint and use the debugger instead of outputting stuff. Interesting. I made a mistake. Yeah, let's flip it down here. I used inverted orders. I defined the method as value first, then index, but I wrote it as index first, then value. And yeah, let's keep it with that. Why did no one tell me? All right, so code work now. Yeah, we didn't have any issues. We added additional elements to the array, 1, 2, and 3. We changed the value of index 1, and if we read value of index 0, we get a 1, which is correct. That's what we added in here. Let's quickly look inside resizing array. The array itself has 3 elements. The first one is 1, correct. The second one is 20, correct. And index 2, the third one is 3, correct. And the size internally is 3 because we're using 3 elements. Makes sense? So at this point, the interesting question would be, do we actually need size anymore? When I add a value, size necessarily needs to be as big as array length. With our current logic, size will never be less than array.length. Because we increase the array size by 1 and then increase size as well by 1. So the length of the array and size both increment by exactly 1 every time we call this method. So they don't change relative to one another. They always stay at the same value. Size is equal to array length at all times. Well, this is the other thing we wanted to get to earlier. This +1 works perfectly fine, but it's not the optimal solution. Think about it this way. When we call the add method and create a new array, we create a new array. The old array is still lying somewhere on the heap. And we have a new array also somewhere on the heap. And then we copy this stuff over. And then we assign the address that is stored in array, that is stored in new array to array. That means we point to the new array from our field array. But the old array that's reserved on the heap, the space that it occupied, is still occupied. It's like losing the reference to an object. That's what the garbage collection is for. It will at some point, after this call is done, after this instruction is finished, start to clear out the space that the old array is occupying on the heap. Might happen instantly if the garbage collection is not busy right now and notices something happening. And if this is happening very fast as well, so objects that are very young are cleared out a lot earlier than objects that have been around for minutes or hours. Garbage collection optimization, don't think about it right now. Thing is, it could also stay around for a while. And this happens right now for every add call. This add means we have a new array and an old array. The old array might get cleared out by the garbage collection, but maybe before we get to that, we call the next add method, or we call the add method again, and we create a new array, and we still have the old array and the old array, and then we make add a third time, or we call add a third time, and now we have a new array, an old array, an old array, and an old array. We have 4 different versions of an array on the heap. And while, sure, right now they don't take up much space, what if we do this in a loop somewhere, because we have to add hundreds of different values? Every time we make a call, we potentially add an additional array to the heap without the old ones being cleared out yet. And maybe the garbage collection doesn't get to that point because you're constantly putting pressure on the heap, meaning you constantly need to access the heap and need to do stuff on there, so the garbage collection has to wait until you're finished. So it doesn't get to touch the heap because it doesn't know if, are you done yet? Can I clean up here, or do you still need the space? And that's a bit of an issue. So it takes up space even if we don't seemingly take up that space. So in terms of program code, it seems like we don't take up that space anymore. We just add 1 byte, or well, not 1 byte, 4 byte, 1 integer in space we need. And the term pure logic. But in the back end, there's still space that needs to be cleared out, and that is still occupied. So we occupy the old and the new space, and then maybe the old, the new, and the new. And next part, every time we call the add method and have to resize this array, we don't only have to reserve additional space on the heap, which might mean blocking space until the garbage collection gets to do its job. We also have to copy all the data over, one by one. Which, again, right now, with only 3 elements is nothing. That's trivial. You can't even properly measure that, I think. Well, at least barely. Depends. With a good setup, yeah. I'm not sure how good benchmarking tools are if they can properly measure something that small. I assume they can. I mean, there are ways you can at least break down the IL and... Okay, it doesn't matter. Let's not think about that. Thing is, though, once we have our hundreds or thousands or millions of entries, well, we occupy all that space, and we have to copy those hundreds or millions of entries over one by one, which takes time. A lot of time, maybe. We have to do that for every add call. So we put extra pressure on the heap, which might run out of space because the garbage collection is constantly busy trying to clean up the space. And our program gets slow because we have to constantly wait for all the data to be copied over. If we're thinking about it, we don't really want this to happen every time we call add. That's just not very good performance-wise. Well, what happens if we don't increase the size by 1, but increase it by, let's say, 10? If we increase the size by 10, that means we use 1 extra space for our new value, but we have 9 extra spaces after that are unused. The total length will increase by 10, but size only increases by 1. So the next time we call add, size will be smaller and we don't have to resize anything. Let's see that in action. Let's set a breakpoint. So if we look down here, array right now has 0 elements and size is also 0. So they're equal. We go into this branch and create a new array, which has 10 elements. We copy over all the data, which is none. And then we set the reference to the new array. So our array internally has now 10 elements. And the very first one gets a value, and we increase size by 1. So after this method is finished, we have 10 elements, all default value 0, but that's not important because the one position we care about, index 0, the very first item we added, is 1, the value we passed on to add. And size is now 1 because we have filled 1 value. Now adding the 2, we have length 10, size 1. So we don't have to go into this branch, we don't have to resize anything, we can just occupy the next space. So we have now 1, 2, size 2, everything is fine, add 3. We can skip it again, set the value, increase size, and yeah, we have added 3 values. but we only needed to resize the array once. And the rest of the code, of course... Oop. Okay, sorry, give me a moment. Okay, we're back. Yeah, somehow shot my active session. And it refused to accept any commands. Like my keyboard was dead. No idea what happened there. I had to restart a few things. Alright, so we're back here. Let's set the breakpoint down here just to check some things after the fact. It's just... You know, a good thing that Writer does autosaves all the time. I don't have to manually save anymore. Save my butt right now. So, yeah, we get value 1 back. That's fine. Resizing array, if we check it, we can still interact with the data as before. Only the internal array has some extra space that is unused so far. But we could use it. That's the point. Question is, what would be the best value to use in here? Like 10 is good right now. I mean, only 1 resize, okay. Ideally, we would do something like 3. But then again, maybe we should just start off with 3 up here, then there's no resize at all. And also, if I add a million different numbers, maybe I should have the size set to 1 million right away instead of increasing by 3, and it's kind of... It very much depends on how I use this class now. If I only add a handful of numbers, maybe a small value would be great. If I add a lot of numbers, a bigger value would be great. And if I know ahead of time how many space I need, why not reserve that space ahead of time instead of resizing at all? Well, for the former, we can do something very simple. Can simply request the size in the constructor. Can still use the default constructor if we don't want that. That's just setting things to 0. But if we know the size ahead of time, we can pass that in. So if we have 1 million elements and we know that ahead of time, we create the array with 1 million elements reserved, no resizing necessary, and no copying. For the second one, however, the amount we resize every time. That is also very much dependent on what you want to do with your class, with your list of data. And there isn't really an optimal answer that fits every situation. You can only find answers that sort of work in many different cases, and that are not too bad. But if we want the perfect resizing, it's best if you code it your hand and make a special class for that one scenario. But something you can do that's somewhat popular, you can take the size and just take the old array length and multiply it by 2. Like that. Of course, in our case, when we start off with a length of 0, that means we get to length of 0 in here as well. So maybe set this to, I don't know, to 1. To make sure that this will always fill in something. Or we could start off at 0 in here and then just make it a minimum. If array length is 0, then use 1 and otherwise double it. Could do that as well. But this is a bit easier. Just start with at least one element. If we don't have this, of course, which, yeah, let's to make sure that it works. And new length. Let's put it like this. Puts array.length times 2. And if a new length is less than 0 or less than 1, then new length equals 1. So, just in case, new length will always be at least 1. Alright. Now with this, if we double it each time, that means if we add only 2-3 elements, then yeah, okay. We maybe have 4 spaces in the array later on. That's fine. Not wasting any space. If we have 1,000,000 elements, well, we maybe start off with 4, length 4, but then after a few adds we had 8, then 16, then 32. At some point we are at 1,000 elements. The more elements you add, the more space you reserve for the next batch of numbers, because you assume that there will be more to come. And of course, that's an issue if you add 1,000,000 numbers and increase the size to 2,000,000. That means, well, if you stop at 1,000,000, you have suddenly 1,000,000 extra in the array that you're not using and wasting away. So that's not ideal. That's why I said the increase is very much dependent on your circumstances. And best case scenario, you don't need to increase at all because you know ahead of time how big it is. But then you don't really need this resizing array anymore because you can use a normal array instead, right? So you could also do this in a sense of, I don't know exactly how much there will be, but I have a rough idea and I make a generous estimate. If I think there will be 1,000,000 elements, maybe I size this to 1,100,000. And if it's a bit over 1,000,000, I still have enough space in here without resizing, stuff like that. So yeah, that's basically one type of hidden array, a data structure that uses an array that's hidden away in private, that lets you interact with the data directly, getting the advantages of an array that's not having too much overhead, at least if the resizing is working properly. But that lets you resize at all. That doesn't force you to know ahead of time how much space you need. So it's a bit of a mix between the linked list and the arrays, if you want. Though that's also not quite fair to say because the way they work and the advantages they bring do differ. It's like a compromise more than anything. But this particular resizing array has another big issue. What if I wanted to store not integer numbers, but doubles. Can't do that right now because it only stores integer numbers. That's hard-coded in there. We use the data type int in the internal array. All the methods use int. It's all based on integer. If we want to store a double, we would need to copy this entire thing and replace integer in certain locations with double. Double in here, double in there, double in there. Value is double, return double, value is double again. This will stay the same. This is a double. And that stays the same. All right. And to make sure we don't accidentally mix the two, let's call one int and the other double, just with the data type in the end. Double, double, make it trouble. And int, like that. So we can have a resizing array double now, which works just fine. We have to change this to double as well. But this should work the same way the integer version worked before. It does. Of course, doubles being weird, it's not 1.1 exactly, but nah, who cares. The details don't matter for us right now. What matters is that it did work. Now I want to extend this to characters. Okay, guess we'll have to copy this again. Can do that. Let's just see, this is char now. I'm not sure what that is. Char. Char, and let's just place double with char anywhere in here. Place, replace. Okay, now we have a char version. Resizing array char. By the way, the double kind of work because the character can be cast to double, but let's not dwell on that. And I made a mistake. Somewhere... Did I? Let's just try it. Alright, so that worked as well. Can expand this to characters now as well. So we have one for ints, one for doubles, one for characters. Though it's a bit annoying to copy this all the time just because I need to store a different type. More annoying maybe even. Let's say I change this. I don't want to double the length. I just want to maybe times 1.5. Just increment it by 50% instead of double it. But then I have to do that manually in here as well. I have to make the same change everywhere. I mean, sure, the code is technically different because this is using double and the other is int, so it's not the exact same text, but essentially it's the same. We don't really care about the data type right now. We don't do anything with value except for storing it, so that's pretty type agnostic. All the rest is entirely superfluous. This entire class is basically the same no matter what type I put in here. I mean, I've just demonstrated how it is always the same, no matter if I use int or double or character. It's just replacing a certain part of the code, literally replacing the text int with double or double with char or car, technically I guess because of character. I call it char, but it's technically character, so car? Should I use car or char? Car sounds weird. Char. Let's keep it a char. It looks more like char, like in chart, and less like car. It's an automobile, even though it's from character. Why is character called character, not character? English is weird. Yeah, in any case, this is a bit annoying. It's certainly doable, and if I don't need to change anything, it's fine, but if I do change something, I need to change it several times, unless I have a special version of the class because a certain type requires different use cases, whatever. There must be an easier way to do this. Because why would I specifically talk about this if it didn't have a deeper purpose? Like, obviously, there is a better version of this. There's a better approach to this, and we can drop all of this and return to this for now. There's a way we can tell the computer, or the compiler, specifically the compiler, that we want to use essentially this class, but with the type in here, and here, and here, and here, and all those places replaced by a different type. We just tell the compiler, simply put in the other variable or the other type name. Like, don't change anything in the code, just use a different type in each of these very specific positions, and do that for every type we need in our program. Like right now we work with characters, so do that for characters. And if we add a second resizing array that uses int, then do it with int. Just use this as a template of sorts. Like, don't use this class directly. Use a copy of this class with the type name replaced by whatever type we need in that situation. And the way we do that is by changing the name. This is no longer resizing array int. Let's also change that down here and here. This is now resizing array with angular brackets with these little arrows left and right, the less and greater symbols. By adding these in the end, we told the compiler effectively that this is not just a normal class anymore. This is now a template for something. This is a template for a resizing array, but for a specific type of resizing array. A type of resizing array that deals with some data type that is currently unspecified. We're just gonna call it T for now. Or maybe type unspecified. I mean, in theory, you could use any name we want. The standard approach is to just use an uppercase T because it's short. Think of it like just question mark. Maybe you prefer uppercase X for the unknown variable, but usually it's T or type. And now we can go through our code and use the same name we used up here in all the places we want to replace stuff with. So we could, again, like that. No, that's not what I wanted. Control C. Could do it like this if I wanted to. But again, T is the usual way to do it. It's simple, and nobody uses an uppercase T for anything else. That's not a legit type name. I mean, you could make one, but I'm not aware of anyone doing that, so that will work. And then we go through our code, and wherever we would replace the type name with whatever type we need, can do this. The return value, the parameters, the internal variable types, can do that in here as well, of course. Place it in here and there and in here, like that. So this is now a resizing array for something, for some kind of data type, unknown data type. Could be anything. Again, could also write X, and then we would use X everywhere to be specified. Maybe let's keep that written out for now to make it a bit clearer. To be specified everywhere. This is not an actual data type. To be specified doesn't exist in our program. This is just a placeholder, like a variable, only it applies to a type now. Maybe it's a bit more like the labels or the aliases we learned about, like could use s equals system. You know, those labels and the using statement. Think of it similar to that. We just determined that to be specified is some kind of alias we can use for something. And the compiler will just insert something, whatever we need in that moment. And what it inputs depends on what we tell the compiler when we need a resizing array. Once we mark this as a template, so to speak, a template for something, it is now inseparable from these angular brackets. This is now part of the name. So when we do a resizing array up here, we also have to add these angular brackets, because this is now part of the class name. And just down here, we have to add something in these angular brackets. But this time, we're not defining a template anymore. We want something concrete based on that template. So I can just insert the type name, character, or char, in here. And with that now I have no resizing array char, just like before. Only it's written slightly different. I have now these angular brackets and the C is now lowercase, but otherwise it's resizing array char. And if I run this code, why do we get an exception? What have I done? What have I done? I guess my change in here was problematic. Oh, because now it could... Yeah, okay, that was my mistake. If we multiply this 1.5, if array length is 0, okay, we force it to be 1, but once array length is 1, we multiply it by 1.5, but then cast it back to int, which means we just drop the 0.5 and go back to 1, which will we stay at. So we don't actually increase the size if it is... yeah, let's change this back to 2. Run the debug again. That was my mistake. Corrupt state? What the hell? Have I completely broken this? No. Okay. So if we look at resizing array char, internally we can still see the array, which is a character array with 4 elements with the 3 characters we specified in our code. It works just fine. But we can also do resizing array double. Do 1.1 again. And what do we do? 2 point... something like that, maybe? Into 3. And 4.456. Whatever. debug it again, and resizing array double has a double array with all the values as intended. And if we do resizing array int, array at 100, resizing array at 101. Well, we now have two resizing arrays. One of them is based on doubles and the other is based on ints. It hasn't. Whoop. Oh, wait. Should resizing array int. Resizing array int. Okay, this is better. One has integer and one has doubles. But they both use the same code. So if I want to change this now to, let's say 20, let's be crazy. Well, then both will use 20 because the same code is used for both. I only changed the template. And let's change this now to just T again, shorten it. And this template is what the compiler will use to create real classes. Now this is important. When we call resizing array double, we don't use this. This class doesn't exist. Inside the runtime, when we run this code, actually before that even, before we run this code, in the binary that we create, when we compile this code doesn't exist anymore. The compiler does not include this weird template class. It will check our code and it will see that we use resizing array once with double and we use resizing array once with int. And so it will create a class based on this. It will copy the entire class here and replace any occurrence of t with double. And then it will create another class where it will copy this entire class, the entire code, and replace any occurrence of t with int. And those classes will be called resizing array double and resizing array int, including those angular brackets. Kind of the real name is a bit more complex, but that's basically it. So it will create two new classes that don't exist in our code here, that are used for these parts in our code. This vanishes when we compile, and instead we get two proper, fully normalized, somewhat normalized classes that each handle a different data type. Of course, it will only create a different type per type we use in here. So if we have a second int array, the compiler will still only create two variations of resizing array, one for double and one for int, because these are still the exact same type. This concept of using a class not by itself but as a template for the compiler to create new classes, this is called generic classes. This is a generic class because it's not specific to a type. It's not specifically int arrays it stores. It's very generic. It could be any type of array. We make it specific when we create an instance of it, when we reference it with a specific name in those angular brackets. Sort of like parameters to a method, we pass on a type into the class name here. We use a generic class, one that is not specific to a type, and the compiler will create new classes that are specific based on this generic. These are very, very useful tools. Generic classes are extremely useful. Generic methods as well. Like these are technically generic methods, but we can have methods that are generic on their own without the class. That's something we might have to look at. When the principle is the same, let's not think about it too hard right now. Let's focus on the class because that's the example I have. And yeah, it's very, very useful because of the same issue we had earlier. We need some sort of behavior that applies to very different types, but it will apply in the exact same way. It will be the same code we use. It's just, you can literally replace the name of the type with the other type and it will still work. But you would have to copy your code several times. And with a generic class, well, we let the compiler do that for us. There are some pitfalls with generics you have to be aware of. For one, it only really works if you can simply replace the type name with any other name and the code will still work. Like for us right now, the only thing we really do that is maybe relevant for the type is the operation here where we assign a value, and here as well. But apart from that, we're not doing anything with the type. We're not calling any functions on int or double that are specific to int or double. If we would do that, well, we can't do that in this generic class. This is the code that needs to be applied to both int and double, so we can't use anything specific in here. It's a generic class. So you're a bit limited on what kind of code you can use in a generic environment. But for something like a data structure, it's perfect. And it's important to remember that the compiler will create new classes. This is not the class we use in the code later on during the runtime. This is just the template the compiler uses. We have two entirely separate classes that are completely independent from another. Resizing array double and resizing array int have nothing to do with one another. They originate from the same template, but that's it. The compiler treats them as entirely independent classes. So if I have public static int some value, like a static field, well, if I do that in here for resizing array double dot some value equals 1, and then resizing array int dot some value equals 2, well, I can still resizing array double dot some value var and resizing array int dot some value, and let's do bool. Let's quickly use the debugger to check those values. As you can see, some value is 1 for the double, which is what we set, and the value is 2 for int, which is what we set. And for bool, which we haven't assigned yet, it's the default value of 0. So despite seemingly being the same field, because they are all referencing this code, they are entirely separate because this class is entirely independent from this class. They are fully separated classes with their own code and behavior and whatnot. The only thing they have in common is their origin, but they're not child classes. This is not a child class of this base class. They don't inherit from resizing array. They are based on the writings in here. There's no inheritance or anything else. You can also do resizing array with struct. Okay, now resizing array might not make the most sense as struct, but you can have a struct that is generic as well. So there's no inheritance going on. These are fully separated classes. They just happen to look the same because they're designed to look the same. That's why they exist. It's the compiler copying the code for us and doing a quick search replace. So generics, very useful tool. You have to be aware of some things, like there are things you just can't do in a generic environment because they are specific to a type, they're not generic. And things like static fields in a generic class are static fields in the class the compiler creates based on that. So different variations of a generic class will have their own versions of those static fields, which sometimes you don't want and sometimes is very, very useful. For me, it's usually very useful to have separate static fields. Don't have to worry about anything intermixing there. But maybe in your case, it's a bit annoying because it sort of breaks the logic of something. But yeah, that's something you should be aware of. There is more to generics. We'll talk about more about the generic methods, which are the same thing, just scaled down. And we'll have to talk about constraints, which is where you can constrain a generic to be something a bit less generic, a bit more specific, which lets you get away with a few things you can't do in this purely generic environment. But that's not for today. The only thing I'm showing you for today is that we don't have to worry about this stuff, because going back to the initial topic, things we can make use of that already exist. This resizing array that we have, this very, very primitive version, already exists in the basic libraries you get when you install the SDK. You just have that. Well, actually not SDK. Technically you have that in the runtime, but yeah, let's not focus on that. First of all, the more general term for this type of thing would be a dynamic array. Hence our name up here. Totally not spoiling anything. So dynamic array is usually the term because it is an array that is somewhat dynamic because it's not a fixed size. Arrays are usually fixed. They have this length exactly. And a dynamic array is, it looks like an array, it behaves like an array for the most part, but it can change size. So it's a bit dynamic, it's not fixed. And many languages have this as a built-in type, a dynamic array or dynamic structures, but in C# it has a different name. We call it simply list. And as you can see here, list itself is a generic class. Because list can be used for any type we want. For integers, for example. Or we can use a list for double. And we can then insert add 1, 2, and 3. And we could also go doubles dot add 1.1, 2.01, doubles dot 3, insert set. Alright, we don't have... I haven't explained that part yet. Do we want to explain that today? It is a bit weird. Do we... No, let's not talk about that today. There's a lot of cool stuff you can do with it. Let's not limit ourselves by doing that in a 10-minute rant really quick at the end of this lesson. So we're not gonna see the equivalent of the set and get value. Though the weird part is that they do exist. But if you remember another thing where we had get and set, which can be made more comfortable, in the same way we can make our get and set from the now dynamic array more comfortable with a different structure. Very similar to the other case where we had get and set. That's all I'm gonna say for today. But yeah, let's have a look at the code. Now they will look a bit differently internally, because different classes, but the fundamentals are there. So the ints will have 1, 2, and 3, and you can see we have a count. The way it's displayed is a bit different. Let's look in here. You can see some more stuff. There's still the original integer array. This time it's called items, not array, but we also have a size. So it is very similar to our code in that regard. So we have the items, 3 occupied spaces, 4 in total, size 3. Again, they look a bit different because internally they work a bit more complex. But the fundamentals are exactly the same. We have an array, we reserve some space, and we use that space up over time when we add new elements. And when we are out of free space in the array, we reserve space for a new array with more space than before. And list itself usually doubles the space. So if we have originally 20 spaces we occupy, we jump to 40. And in here as well, you can say you want to start out with a large number of exactly this many items in there, this much space, and that's what the array is going to initialize with. Unlike our case, list by default will initialize with 4. That's hard-coded. So that's why our arrays in here are also length of 4, the actual arrays internally, because that's what they start off with, not with 0. So there we have it. If you need to store a lot of values and you don't know exactly how many, you're probably gonna end up with a list. Or maybe a data type that's very similar to list in structure, but has slightly different ways to access the data internally. And I think that is for next time, alongside the special get and set way, and probably a bit more generic. It will end up with a few details and constraints. And with that, I'm gonna end it for today. As I mentioned, I do not know how the new schedule will work out. I haven't found any time I can do it regularly. Like, I think the weekends are out, so I would have to do it someday during the week, but I'm busy during the day because I have to go to work, and I'm busy in the evenings because of private stuff, and so I'm not really sure when I will have time to slot in, well, effectively 2 hours, because even if the stream is only 1.5 hours, I always have some additional time I need to set aside before the stream to make sure the IT all works out. Technology is sometimes a bit iffy. So yeah, we'll see. Hopefully I will find something. And if not, well, we'll have to do that a bit more irregular. I mean, most of you watch only through the VODs anyway, so it's not like we lose anything. Okay, so at least with my time zone, I wish you have an enjoyable evening. If you're not my time zone, maybe good morning. Enjoy the day. And see you next time.